Hello, everyone. To my new subscribers, thank you for subscribing. I always appreciate that. Much awaits you here on this channel. And this morning, as I was thinking of what video to prepare, because I had three topics really. One of them was the difference of the special products one. Remember that I only gave you a part one of that. The other one was we still have pending the logic video, but I haven't gotten around to it because, by the way, for those of you who are new to the channel, I will tell you this: I'm mostly off grid for the most part. What I mean by off grid is that pretty much most of my day is taken up by other pursuits. I like to be outside. I like to be interacting. I'm not really a type of person to be sitting in front of a screen all day long. And the only reason I started the YouTube channel really is because I wanted to share mathematical knowledge because I know that there's a thirst in the world, and here in the United States specifically, particularly because of our very terrible educational system. There's a lot of people who want the rigorous truths of mathematics, and so I'm here to provide you with that. But for the most part, I'm an off-grid sort of person. I have very relaxed. I have a very relaxed lifestyle. I put my faith in God, and I let God do most of the work, but always, of course, being mindful that I also have duties. But my days are pretty much are very structured days, and they really are filled with peace and joy. But so I thought of since the video yesterday was quite popular, I decided to just continue that at least for today's Saturday. Tomorrow is Sunday, and so you'll have my Sunday message. There'll be some kind of message I haven't decided yet on morality, because we do need to step up the game on morality in the Western world. But as I was thinking of ideas for this particular video, I was thinking back on the joys of college, especially my undergraduate experience. And I was reminded of a Pine email. If you're of a certain age, you know what Pine email, you know exactly what I'm talking about. I actually still use it, believe it or not. All my emails come through in a terminal. But I was thinking of a Pine email I received decades ago when I was a freshman at Columbia University. If you don't know me, you're new to the channel. I did my undergraduate degree in math. I majored in math at Columbia University in New York, and I also minored in political science, specifically international relations. But when I was thinking of, I received this email when I was a freshman at Columbia. And being a math undergrad is not merely about the long hours of solitary work, nor is it the seemingly endless cycle of caffeine fueled or other substances, some people, delirium that marks your time. Nope, not for me anyway. What truly elevates the experience is sometimes unexpected, such as random emails from classmates. And there was one email I received that still lingers in my memory. You see, I was enrolled at the time. I made it into, even though I had taken AP calculus in my high school, I made it into honors calculus at Columbia because the reason for that being that I knew they used Spivak's calculus book. Although my back then my instructor used to pronounce it as Spivak. Some people pronounce it Spivak, and that kind of stuck with me sometimes. But I think it's Spivak. I think so. But anyway, I was in honors calculus, and at that time, one of the classmates was not really a math major, but really an engineer. No offense intended, by the way. Classmates often used to email me because I was really known as someone who was, and I'm still known as that. I'm very no nonsense. The classmates used to know me as someone very professorial, quote unquote. I mentioned this also because a lot of people in life ask me if I've been asked all my life, ever since I was in high school, if I'm always so formal. I get that all the time. It's so unexpected sometimes. I go out shopping. Sometimes I might go to the grocery store, and I often get asked, "Are you working today?" If it's a weekend or something, and no, I'm not. Well, I am working doing certain things, but not. They mean if I'm actually in a corporation or something, and I always, the answer is no. And then they say, oh, because you look so formal with your tie. And so I always get that. And as far as I can remember, I have always been a classical person, classically dressed in some way. In fact, I don't ever recall ever owning a pair of shorts, let alone going out in shorts. And by the way, I don't say this to come across as a snob, but just to give you an idea that even as an undergrad, I had my own particular way of seeing the world, a very specific philosophy about dress. I think it's important that you young people, if you're watching this channel, whether you're a Christian or not at this point, you should have a philosophy of life about certain things. You should have standards about why it is what you do. Because if you don't, why even bother to be a mathematician in the first place? You have to be able to rationalize everything that you do. And that's why I'm always so strict about certain things. And if you ask most people why they dress the way they dress, they won't even tell you. They might, at best, they might tell, oh, I just like it. That's not the reason why, I particularly dress a certain way. There's a philosophy that comes with it. It's in my case, it has to do with both the way my definition of self-respect and self-love, and also respect towards others. I do own, by the way, a pair of jeans, and those are good for horseback riding, or if you're doing something like on a trail or some gardening or something. But there's something really nice looking, I agree, about a nice pair of, Southwestern style cowboy boots and a pair of jeans, as long as you're neat, clean cut, and clean all around, of course. But anyway, going back to the student, he was inquiring about a homework problem that contained the variable x, which, as was quite explicitly stated in the assignment, was a real number. And yet he did not simply accept this, as one should, given the context. He asked me, he said, inadvertently, assume that x is really a number. Now, at first glance, I'll admit I was tempted to send him a response, suggesting that perhaps he should really reconsider his career in mathematics. I mean, after all, he was an engineer, a self-described engineer. Get out of my math class. Just joking. But no, I saw an opportunity there, because he asked a well-meaning, but really he was profoundly misguided in the phrasing because he didn't mean it. And he inadvertently asked a question worthy of a good mind. What precisely is a number? And we started that question yesterday. You see, if we are to seriously entertain the notion of incorporating into our number system all the possible lengths of triangles, the delightful intricacies of square roots, or the abstract beauty of limits in calculus, the rational numbers simply do not suffice. We need more. Now, I don't want to speak in vague terms. Rational numbers, they're charming, infinitely dense little things, are almost, at first glance, almost sufficient. But almost does not quite cut it. They have their limitations. They are, in fact, little more than a stepping stone towards something much greater. The real numbers, yes, the reals. Now, those are what we need. But what exactly do the reals possess that the rationals so dearly lack? It's quite simple, really. I admit you might struggle with this. But it's elementary enough for the faintest spark of intellect to catch. There are three key properties that stand out, that glare at us like beacons of truth. First, there are infinitely many rationals. And if you studied abstract algebra, you know full well that the field axioms do not guarantee an infinite set. Indeed, there are many finite fields. Second, they are ordered. And yes, ordered, not a cacophony of madness. Not only are the elements different from each other, but given any two different ones, one is bigger than the other. So we need to add the less than or greater than symbols to the mix. And third, we desire metric properties. And that is how far from zero and the distance between two numbers. And thank God there exists in all the elegance of our discipline a single beautiful axiom that is so simple, so straightforward, that it will encompass all of these properties without introducing any new functions, operations, or needless complexity. The simpler and more elegant your axiomatic system, the more general and appealing your theory is. And how can we do this? We define a subset of the field known as the positive set P, and it behaves precisely as you would expect positive numbers to behave. Marvelous, isn't it? It's simple, it's precise, and it's absolutely unbeatable. So, what does the axiom look like? Well, let's have a look. Right, so hopefully you can see on the board, this is the axiom. An ordered field is a field, F, along with the following additional axiom known as the order axiom. There is a non-empty subset P of F called the positive elements, such that if A and B are elements of P, then A plus B is an element of P, and A times B is an element of P. Also, if A is an element of the ordered field and A does not equal 0, then either A is an element of P or negative A is an element of P, but not both. Why is this enough? I want you to think about it for a moment. Think about why that would be enough, and let's talk about it. So why is this enough? Well, if we think about the number 1 as being positive, and by the way, if 1, that means that 1 plus 1 would be positive, 1 plus 1 plus 1 is positive, and if of course 1 is not positive, then it would be a contradiction. It would contradict part B of our axiom here. Negative 1 would then be positive. But then for any positive A, if we look at part A, we would deduce that A times negative 1 would be negative A, which is also positive in that case, and then it would contradict part B of this. So for positive elements are really all you need here to define the absolute value. And really enough by that to give metric properties. So we have to begin with a formal treatment of this by defining what the inequality is. And so here is another definition. Have a look at it. And as you probably anticipated, the real numbers represent an ordered field. And you may use any of the standard properties of inequalities. And these are the properties of inequalities. I won't make you prove them. You've probably, if you're watching this series, I'm sure you've been tortured at some point of your undergrad career to prove those theories, to prove them, those properties. But here they are, in case you need that review. So the question is, how does defining an ordered field with positive subset P give us a distance function? Well, really, we need another. It all comes down to the absolute value function, which we will look at now. So here we are, the absolute value function. Now, you might think it's a little odd to see, you notice how you have negative x in there because the absolute value function is supposed to make everything positive. But the point is that for those x values, x is going to be less than 0. So x already has a negative sign. And of course, one way to get rid of the negative sign is to add another negative sign, right? Negation. So would you cancel out the one x that's already that x already has? So just to give numerical examples, if I gave you, let's say, the absolute value of x equals x when x is greater than 0. Well, you already know that, right? Absolute value of 7 is 7. Absolute value of 2 is 2, etc. But what if you had the absolute value when x is less than 0. Well, in that case, we have negative 7, which equals negative parentheses negative 7, which gives you back 7. So that's really the difference there. Now, you may use all the standard properties of absolute values without proof. Many of you have already proven them. If you've taken an intro to proofs classes, you have proven them. But I wanted to include. I do want to do a proof on these on these three here. I originally had a lot of them, but I decided to keep these last three here. So one of them is called if you look at number 2 here, the triangle inequality. And you also have the reverse triangle inequality. So you have A and B, of course, are elements in an ordered field like the real numbers. All right, so let's prove the number 1. So the first thing is we first have to assume that the absolute value, let me bring this down actually. Okay, so we have to assume here the absolute value of A is going to be less than or equal to B. Now, if we multiply here both sides by negative 1, you will also see that the absolute value will be, bring down that negative here. Now you have this relationship. Now, if we say that negative A, negative absolute value of A, is going to be less than or equal to A, which is less than or equal to the absolute value of A. So we can place these three facts here that we have, place them together. So that means we can rewrite this as negative B is less than or equal to the absolute value, negative absolute value, A, and that's going to be less than or equal to A, which is going to be less than or equal to absolute value A, less than or equal to B, just B. All right? And that what does this imply? Oops. Bring down the page here. What does this imply? Well, you should be saying that negative B is less than or equal to A, and that is in turn is less than or equal to B as you desire. Now, if you want to prove the backwards direction, you have to assume that negative B is less than or equal to A, which is less than or equal to B. So in this case, we can use that A is less than or equal to B. All right, what about the second proposition here? The second, the triangle inequality. First, I want you to try it, and I recommend using scrap paper. Because more so than in any other math course, you should always be, when you're dealing with real analysis, it really is helpful to do some scratch work before your proof. And that really is the case for a few reasons. One of them being, in many of our proofs and in many of your problems, you discover the proof by starting with what you're trying to prove and then working backwards to reach things that you already knew, either from known properties, from other theorems, etc. So I want you to try it first and then see what you come up with. All right, here is the proof. So we have the triangle inequality, and by our last proposition, this is true if and only if these conditions hold. Now you can break apart these sums into two of them. And when you do that, you can then begin to construct your proof. We have x and y as an element of an ordered field. We have the following statements. If we add them together, we thus get this. And thus we have proven our theorem. Really surprisingly, by the way, the triangle inequality is a very important tool in analysis and will be used over and over again. It's called the triangle inequality because of vectors, and I drew a little triangle. I hope it comes out. There we go. Because we have the vectors that form a triangle. Remember, a vector has a length. So if you think about the hypotenuse here, and if we put it as the absolute value of x plus y, and this being y, of course, and we could call this triangle ABC. And so we have here x, here we have y. So if you take a pair of vectors and also consider the vector x plus y, then we have the lengths of each of these. Now, the shortest route between 2 points on a plane is a straight line. You know that from geometry. And so the distance from A to C is here. That's the distance from A to C. And that is the shortest route to get from A to C. It's clearly a longer route if you go from A to B. And then from B to C, which of course is of distance, x, the absolute value of x plus the absolute value of y. And that is precisely what the triangle inequality says. Now, what are the consequences of the triangle inequality? It has some nice corollaries, we call them. A corollary, by the way, there are other theorems that follow quickly from it. Can any of you think of what the corollaries might be? All right, so we have a corollary here of the reverse triangle inequality. And this is not my proof, by the way. It's a pretty standard proof you can find in most sources online. I didn't have time this morning to do my own, but this is just so you get an idea. So have a look at it and see if it's similar to what you came up with. All right? And now we have more corollaries. Based on, these are consequences of what we've proven, by the way. And based on these corollaries, we now get to really something very useful and interesting, which is the distance function. Here is the distance function. And with that, we have really described all of the axioms of the rationals. And in fact, to capture the reals, we only need to add a single additional axiom. And that is called the completeness axiom, which we'll be looking at in our next video in this series. And that axiom will fill the holes in the holes we were talking about in the rational numbers. I hope you all have a blessed day. I hope this was useful to you. If it was, as I always say, please subscribe to this channel and continue to bless me with your presence. And hopefully the Sunday messages are also valuable to you if you care about maintaining a certain code of morals. Thank you all.